Welcome back. Let's practice finding absolute extrema for regions in 3D space. Alright, so here's our first example. We want to find the absolute extrema of the function over the region. And we're given the multivariable function f of xy is equal to the quantity 2x minus y squared and the region that includes x and y values such that x is between 0 and 1, including both 0 and 1, and y is between 0 and 1, also including 0 and 1. Okay, so in order to find or locate the absolute extrema of a multivariable function over a region, we have to consider three different types of points that have the potential to be the absolute maximum or minimum for the function on the region. The first type of point we have to consider are any critical points of the multivariable function itself. The second type of point are the endpoints of the boundaries that make up the region that we are working over. And then the third type of point are any critical points of the boundaries of the region. All right, so our goal here is to find all of those points for this function on this region. And once we have them, we will compare their z-values. And the point with the smallest z-value will be the absolute minimum. And the point with the highest z-value will be the absolute maximum. Okay, but what I recommend that we do first is draw a graph of the region that we're working with. So let's do that here. Our regions will always be contained in the xy plane unless we're told otherwise. So I'll draw an x-axis and a y-axis here. This is the x and this is the y. And the region that we're working with here is the region that includes x values from 0 to 1 and y values from 0 to 1. Okay, so if this is x equals 1 right here, and this is y equals 1 right here, then any points in the xy plane that are in the first quadrant and don't go above y equals 1 or past x equals 1 will make up the region that we're working with. Okay, so you could draw a line here at x equals 1 and a line here at y equals 1, and you would find that the region that we're working with is a square region. Okay, this square would be the region R that contains all the combinations of x and y coordinates for the points on this function where we're looking for absolute extrema. And so now that we have drawn the region, we also want to label the endpoints, or where any of these different boundaries meet, right? Each of these lines represents a different boundary for this region. This line is the boundary y equals 0, this line is the boundary x equals 1, this boundary is y equals 1, and this boundary is x equals 0. All right, these 4 points where those lines or those boundaries meet would be endpoints that we will eventually check to see if they are absolute minimums or absolute maximums. All right, so you want to label all of those points just like this. This point is the point 1, 1. This is the point 1, 0. This is the point 0, 1. And this is the point 0, 0. Okay, so we'll come back to those endpoints, but before we work with them any further, what I like to do once I've drawn the region is look for any critical points, and remember that multivariable functions have critical points where their first partial derivatives are both equal to 0 at the same time. All right, so what we need to do is find the partial derivatives with respect to x and y of this function, set them equal to 0, and then solve for x and y. That will give us the critical points for this function. And once we have those, we just want to consider any of the critical points that are within this region as potential points that will be absolute extrema for the region. Okay, so let's find fx and fy, starting with fx. Let's take a partial derivative with respect to x of this function. And we will have to use the chain rule here because we do have an expression of x inside this quantity being squared. So take the derivative of the outside function first, multiply that 2 down, keep the same inside function, subtract 1 from the exponent of the quantity, so it's just to the power of 1 now, and then don't forget to multiply by the derivative of the inside function. And the derivative of 2x minus y with respect to x will just be 2. The derivative of 2x is 2, and the derivative of negative y is 0 because y is a constant with respect to x. All right, so we multiply by 2, and so simplifying, 2 times 2 is 4, so distribute 4 through this quantity, and you will get 8x minus 4y. Okay, and then we do want to set that equal to 0 and solve, but before we do that, let's find fy as well. Let's take the partial derivative with respect to y of this function. The derivative will start out the same because an expression of y is also inside this quantity being squared. So use the chain rule, multiply that 2 down, keep the same inside function, and then multiply by the derivative of the inside function, which with respect to y will be negative 1, because 2x is now a constant with respect to y. Its derivative is 0, and then the derivative of negative y is negative 1. So we multiply by negative 1. And so simplifying, 2 times negative 1 is negative 2. So distribute negative 2 through this quantity, and you will get negative 4x plus 2y. All right, and we also want to set that equal to 0 and solve for x and y, right? We now have a system of equations that we need to solve. So let's work on that here. Typically, my method is to solve for one variable in one equation and then plug in what it's equal to into the other equation. And so let's solve for y in this equation. If we add 4y to both sides, we'll have 4y is equal to 8x, and then dividing both sides by 4 gives you y is equal to 2x. All right, and so now, if y is equal to 2x, then we can plug that in for y in this equation and solve for x. Okay, so if we do that here, we will get 0 is equal to negative 4x plus 2 times y, where y is 2x, so we're multiplying by 2x. And so simplifying, we get negative 4x plus 4x, which is 0, right? Negative 4x and 4x cancel each other out, so we get 0 equals 0, which is not all that helpful, right? We're not able to solve for x here, and because of that, we're also not able to solve for y. At least we're not able to get a specific number for either of those variables. So what's going on here? Why did this happen? Did we make a mistake, or is this okay? Well, what's actually going on here is these two equations would represent the same exact line, right? If you were to solve for y in this equation, watch what happens. I'll do this on the side. We're starting with 0 equals negative 4x plus 2y. If you subtract 2y from both sides, you get negative 2y equals negative 4x. And if you divide both sides by negative 2, you'll get y is equal to 2x. So both of these two equations are exactly the same. They represent the same line, that line being y equals 2x, which means that any values of x and y that make that equation true will be values of x and y that make both of the partial derivatives equal to 0. Okay, so what we find here is that y equals 2x is a solution. Any points along that line will be critical points for the function, because any points on that line will make those partial derivatives 0 at the same time. So we will have to consider all the critical points along that line in this region as potential points to be absolute extrema. Okay, but to actually be able to conclude anything about those points, we do have to know what their z-values would be when plugging them into the multivariable function. And so what we can do here is just plug in the line y equals 2x in for y in the function, and that should give us an expression that tells us what the z-values will be for those points. All right, so as a little bit of side work here, we're going to look at f of x 2x, right? We're still keeping x as x, but then for y, we're plugging in 2x. And so the function evaluated at that line will give you 2x minus 2x squared, right? We're just replacing y with 2x. And 2x minus 2x is 0, so this is equal to 0 squared, which is 0. And what that means is that all of the points along this line, or any coordinates of x and y that make this equation true, will have a z-coordinate of 0. The output for the function will be 0 for any points along that line. Okay, so that's the z-value for those points that we want to be comparing to all of the other points that we find that have the potential to be absolute extrema for the region. All right, so kind of a tricky start to this problem, but if you are looking for a more basic example to start with, feel free to go back to my lesson video on this topic and watch that first if you haven't already. But again, what we have found here is that any points along this line will be critical points for the function, and they have an output value of 0. Okay, and if you want to get a better idea of how many points that really is, remember that we are working within this region, so you could graph this line, y equals 2x, and you could see exactly what points are going to be included. And so this is a line with a slope of 2 that would have a y-intercept of 0 because there is no constant here. So what we could do in our graph here is draw a line with a slope of 2. So you would rise up 2, move over 1, rise up 2, move over 1, and that would be the line y equals 2x. Okay, so I'll draw that here. That line would extend forever in this direction and this direction, but I'm just drawing the part of it that would be included in the region. So all the points along this line are critical points of this function that we have to consider for absolute extrema. And you can see that for that line, the values of x that can be used for it are from 0 to 1/2, right? Halfway to 1. And if you're not good at drawing an accurate graph or an accurate region, what you could do to figure out what values of x in the region correspond to this line, y equals 2x, is just work with the boundaries you've been given. Plug in the lower bound of 0 for y, and then solve for x. That will give you one of the endpoints for x. So if y is 0, 0 is equal to 2x. Solving for x, that would give you 0. And then using the upper bound, if you plug in 1, you'll have 1 equals 2x. Divide both sides by 2, and you'll get x equals 1/2. So we know we're working with this line, but just for the values of x from 0 to 1/2. All right, so I'm going to write down for 0 less than or equal to x, which is less than or equal to 1/2. That describes all the critical points for this function on this region that we need to consider. Okay, so that takes care of our first type of point that we need to consider, which are critical points on the multivariable function. We have found them. They all have output values of 0. But now we need to consider the other types of points, starting with the endpoints of our region. All right, so what we want to do here is plug in the endpoints into the multivariable function and see what values of z we get. And our 4 endpoints are 1, 1, 1, 0, 0, 1, and 0, 0. Okay, those are the 4 endpoints of our region that we identified earlier. What we want to do is plug all 4 of those sets of coordinates into this multivariable function and see what the output would be. And I'm not going to write out that work explicitly, but if x and y are 1 and 1, you will get an output of 1. So that would be the z value for that endpoint. If x is 1 and y is 0, and you plug that into this function, you will get a value of 4. And then if x is 0 and y is 1, and you plug that into this function, you'll get an output of 1. And finally, if x and y are both 0, hopefully you can see if you plug that in here, you will get 0. Okay, so now we have checked the z values for the endpoints of our region, which means there's only one more type of point that we need to check, which are any critical points along the boundaries of our region. And so we have to take turns looking at each of these boundaries and identifying any critical points on the curves that make up those boundaries in 3D space. And so that's what we're going to do next. We're going to take turns looking at each of these boundaries and identifying any critical points. And there are 4 of them. And so let's start with this one up here. I'll call this boundary A. And for that boundary, notice that y is always equal to 1, and the value of x for those points just depends on what value of x you're at along the x-axis. So what we're going to do here, in order to look at that boundary curve, is let x equal x and y equal 1. Okay, again, we're letting x equal x, because as you move along this curve, the value of x is just based on where you're at along the x-axis, and then y equals 1 because this would be the line y equals 1. The value of y is always 1. And what we're going to do is redefine our multivariable function using x equals x and y equals 1. So we'll get f of x, comma 1 instead of f of xy, and then plugging in x for x and 1 for y, we'll get 2x minus 1 squared, right? 2x stays the same, but then we subtract 1 instead of y because 1 is y. Okay, and so this right here represents the equation of the curve that would make up this boundary in 3D space. All right, remember that we are working with a surface in 3 dimensions. This region that we've drawn here is just showing us the different x and y coordinates that we're considering for points on the surface, but then these actual boundaries of the region, as you slice through the surface, will not just be straight lines, they will actually be curves that could have critical points where absolute extrema could be located. All right, and so remember, to find any critical points of a curve, this is a Calc 1 concept, we have to take the derivative of that curve, set it equal to 0, and then solve for x. All right, so let's take the derivative. We'll have f prime of x1, and that will be equal to the derivative of 2x minus 1 squared. Use the chain rule, multiply that 2 down, subtract 1 from that exponent, so it's to the first power, and then multiply by the derivative of the inside function, which is 2. And so simplifying, we get 8x minus 4. All right, and then set that equal to 0 and solve for x. So adding 4 to both sides gives us 4 equals 8x, and then divide both sides by 8 to solve for x, and you'll get x equals 1/2. All right, so x equals 1/2 is the x coordinate of a critical point on this curve or on this boundary that would have the potential to be an absolute maximum or minimum. Now its corresponding y coordinate will be y equals 1 because for this curve, y is equal to 1. So any points along that curve will have that y coordinate. So x equals 1 half, y equals 1 is the critical point in question here. But you do want to check to make sure that that would be in the region, right? Sometimes you could find a critical point on this curve that is not included in the region that we're working with, so just make sure that the coordinates would be inside of that region. And so x equals 1 half, y equals 1 would be, that would be the point right here. Okay, x equals 1 half, y equals 1. So let's check the z-coordinate of that point because we'll need to compare that to all of the other points we're finding to determine which is the absolute maximum and minimum. So our critical point here is 1 half 1. And if you plug that into this multivariable function, where x is 1 half and y is 1, you will get an output value of 0. Okay, and that should make sense because that point is actually on this line, y equals 2x, that we found earlier, which are all critical points of the actual surface, and all of those points had outputs of 0. Okay, so that checks out. Technically, that's not a new point that we just found, but you still want to check it anyway. All right, so that's it for boundary A. Now let's move on to the next boundary. Let's work on this one here. I'll call it boundary B. And for boundary B, the value of x is always 1, right? This would be the line x equals 1. And the value of y depends on where you are along the y-axis. So we're going to let x equal 1 and y equal y. And so our multivariable function, when x equals 1 and y equals y, will look like this. We'll have 2 minus y squared, right? If x is 1, you'll have 2 times 1, which is 2, and then y staying the same, so we have 2 minus y squared. Now let's take the derivative of that function. F prime of 1y will be equal to 2 times 2 minus y to the first power times negative 1, right? That's just using the chain rule. Took the derivative of the outside function to get 2 times 2 minus y, and then multiplied by the derivative of the inside function. And so simplifying, you'll get negative 4 plus 2y. All right, so now that we have the derivative of that curve, specifically this curve, which represents this boundary, we want to find any critical points. So let's set that derivative equal to 0 and solve for y. If you subtract 2y from both sides, you'll get negative 2y equals negative 4, and then dividing both sides by negative 2 gives you y equals positive 2. So y equals positive 2 would be the y-coordinate of a point on the boundary curve that is a critical point. And its corresponding x-coordinate will be x equals 1, because for that boundary, x is equal to 1. So we have x equals 1 and y equals 2, giving us a critical point of 1, 2, but that point is not in our region, right? You always want to check this. You want to check if the critical point you find for a boundary curve is actually in the region, and the point 1, 2 would take you outside of this region, right? We're not working with any values of y bigger than 1. Y has to be between 0 and 1, so this is not in the region. So that point is not in contention for being an absolute max or min for this function over this region. All right, but that's it for boundary B. Let's move on to our third boundary. Let's look at this boundary right here. I'll call it boundary C. And for boundary C, notice that y is always 0, and then x is just whatever value of x you're at along that x-axis. So we're going to let x equal x and y equal 0. And so rewriting our multivariable function, where that is the case, we'll have f of x 0 is equal to this expression, but where x is x and y is 0. So if y is 0, you're just going to have 2x squared, which is 4x squared. All right, so that's the curve for that boundary. But now let's find any critical points for it. Let's start by taking the derivative of that function, and you'll get 8x. That's the derivative of 4x squared. And then setting that equal to 0, we get x equals 0. Okay, so that's the x-coordinate of the critical point. It would be paired with y equals 0, because that's what y is equal to for that boundary. But that's a point that we already checked, right? X equals 0, y equals 0 is one of the endpoints that we checked earlier. It has a z value of 0. So this is not a new point. There's nothing to check here. We've already accounted for that potential location of an absolute max or min. So let's move on to our last boundary, which will be this boundary that I'll call boundary D. And for boundary D, notice that x remains constant at 0, but then the value of y depends on where you are along the y-axis. So we're going to let x equal 0 and y equal y. And so plugging those into the multivariable function, we'll have f of 0, y, x is 0, y is y, and that will give us the function of 2 times 0, which is 0, minus y, so negative y squared, which is just y squared. All right, so then take the derivative of that, and you'll get 2y, and set that equal to 0, and you'll get the value of y equals 0. And so that's the y-coordinate of a critical point on that boundary, but it's the same point that we looked at before, right? Because this y equals 0 would correspond to this x equals 0, because this boundary is located where x equals 0. And so the point is x equals 0, y equals 0, which we already checked before. It's one of the endpoints. All right, so that's the same as before. We didn't find any new points to consider as potential absolute minimums or maximums for the function over the region. But now we've checked everything. We checked the critical points of the multivariable function itself, we checked the endpoints of the region, and we checked all the critical points of the boundaries of the region. Now we just have to compare all the different z-values for those different points. And really, all we have to consider are the endpoints here and the critical points along this line for the function. Okay, our boundaries did not produce any new points, so we don't have to worry about considering any of those. And so looking at the z-values, we have 1, 4, 1, 0, and then 0 for all of those critical points. So 4 is the biggest, which means that this point 104 is the absolute maximum. So I'll write that down. We have an absolute max at the point 104. And then what about the minimum? What is the minimum z-value? Well, we have 0 here and 0 here. And this point 0, 0 would actually be included with this line that has all those critical points with the z-value of 0. So we can include all of those points like this. We can just say that there are absolute minimums along y equals 2x for 0 less than or equal to x less than or equal to 1/2. And so y equals 2x over this interval includes all of the points that would be absolute minimums for this function over this region. All right, and so that would be the final answer to this example. It took a lot of work to get there. These are fairly lengthy problems, but hopefully you find that the calculations themselves are not too difficult to do. You just have to remember to stay organized and keep track of all the different points you find and their z-values so that you can compare them at the end. All right, but that's it for this example. Let's take a look at another one. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we once again want to find the absolute extrema of the function over the region. This time we're given the multivariable function f of x, y is equal to x squared minus y squared, and our region R includes x and y values such that x squared plus y squared equals 4. Okay, so this is a little bit different because in our previous example, we were just told that x is between these two values and y is between these two values. But here, we are just given an equation, x squared plus y squared equals 4. That's the region. And so that can seem intimidating at first, but if you look at this equation, all this is the equation of a circle, right? X squared plus y squared equals 4 is in the form of a circle centered at the origin of the xy plane with a radius of 2, right? You have x squared plus y squared equals the radius squared, and the square root of 4 is 2. So if we draw our region here, which is what I always recommend you start with for these problems, here's my y-axis and here is my x-axis, and I'll label them here. This is the y and the x. The region that we're working with here is a circle centered at the origin with a radius of 2. So if this is x equals 2, y equals 2, x equals negative 2, and y equals negative 2, our region will look something like this. Okay, that is the region R that we were considering for this function. But now it looks like in this case that there are no endpoints. right? This is seemingly one continuous boundary because it's a circle, it's one curve. But from the perspective of being a function that we can work with of y in terms of x, we would actually have to split up the circle into two curves, right? Because x squared plus y squared equals 4 is technically not a function. It just represents the graph of a circle. And the reason it's not a function is because it would fail the vertical line test, right? You can draw a vertical line through this curve multiple times and hit 2 points. That's not good for a function. So what we would actually do here is solve for y in this equation. So if you subtract x squared from both sides, we'll have y squared equals 4 minus x squared. And then take the square root of both sides, you'll get y is equal to plus or minus the square root of 4 minus x squared. And so the positive square root of 4 minus x squared represents the top half of this circle. So that would be one curve or one boundary. And then the negative square root of 4 minus x squared would be the bottom half of the circle or the second boundary. Okay, so I'll label that here. On the top half, we have y equals the square root of 4 minus x squared. And on the bottom half, we have y equals the negative square root of 4 minus x squared. But what's important about that is that we do have two endpoints then, because endpoints occur where two boundaries meet, and so that would be right here and right here. The top half of the circle meets the bottom half at those 2 points. So the two endpoints for this region that we will have to consider as potential locations of absolute extrema are the points 2, 0 and negative 2, 0. Okay, so keep that in mind. But before we check those endpoints, you don't want to forget to check for critical points on the surface itself. So let's find the first partial derivatives and set them equal to 0 and solve to see if there are any critical points we have to consider. So starting with fx, let's take the partial derivative with respect to x of this function, which is pretty quick. Just take the derivative of x squared and you get 2x. The derivative of y squared would be 0 because it's a constant with respect to x. And then a very similar thing will happen for fy. If you take a partial derivative with respect to y of this function, x squared will become 0 because it's a constant with respect to y, and then negative y squared, the derivative of that is negative 2y. All right, and so setting both of those equal to 0, we'll have 0 equals 2x and 0 equals negative 2y. Solving for x and y there, we get x equals 0 and y equals 0. So we find one critical point here. The critical point is at the point 0, 0. And so let's check to see if that's in the region we're working with here. And it is. 0, 0 is the origin of the xy plane, and that is inside the circle. So we can check that off. It is contained within the region. And so you do want to plug it into the multivariable function to get its z value, because we're going to compare that to the other points we find later to see where our absolute extrema are. And so plugging in 0 and 0 for x and y here, you'll get an output of 0. That's the z coordinate for that point. All right, so we're done with that. We have now considered the critical points of this multivariable function. Now let's check the endpoints, and we only have 2 of them to check this time around. So let's do that here. Checking the endpoints, we want to check the following 2 points of 2, 0 and negative 2, 0. And so when x equals 2 and y equals 0 for this multivariable function, you'll get positive 4, and you'll actually get the same thing for negative 2, 0 as well. If you plug x equals negative 2 and y equals 0 into this function, you will get the z coordinate of 4. Okay, and so that's it for the endpoints. We only had 2 to check, which means there's only one more type of point that we have to consider, which are any points along the boundaries that are critical points. All right, and we do have 2 boundaries to check. We have the upper half of the circle, which I'll call boundary A, and then we have the lower half of the circle, which I'll call boundary B. And so let's start with boundary A. For that boundary, we would just let x be whatever value of x you're at along the x-axis, but then the values of y for that curve depend on this equation. So we will let x equal x and y equals the square root of 4 minus x squared. All right, so let's plug that into our multivariable function. We'll have f of x comma the square root of 4 minus x squared. So we're going to replace y with that expression, and we'll have x squared minus y squared, where y is the square root of 4 minus x squared, which means if we simplify, we get x squared minus 4 minus x squared. And remember to keep that in parentheses until you distribute this negative, because you are subtracting this entire expression. And so distributing that negative, you get negative 4 and positive x squared. So combining like terms, you get 2x squared minus 4. All right, and then take the derivative of that so that we can solve for x and find any critical points. So we'll have f prime of x comma the square root of 4 minus x squared, and that will be equal to 4x, right? That would be the derivative of 2x squared, and the derivative of negative 4 is 0. And so setting that equal to 0, we'll have 0 equals 4x, which gives us that x is equal to 0. Just divide both sides by 4 and you get x equals 0. And so that would be the x-coordinate for a critical point along this curve. But what would be the y-coordinate? Well, it's going to be based on what y is equal to for that boundary. And y is equal to the square root of 4 minus x squared. So if x is 0, you'll have 4 minus 0 squared, which is 4, and the square root of 4 is 2. So you get x equals 0, y equals 2. Okay, so the critical point that we find here is the point 0, 2, which is contained in our region, right? You want to check that. The point 0, 2 is this point right here. It is along that boundary, as we would expect. And so you want to plug that into the multivariable function to get its corresponding z value. And if you plug 0 in for x and 2 in for y, you will get negative 4. That is the output, or the z value for that point. And I am going to put a little check mark here to indicate that that point is in this region. All right, but that's it for boundary A. That's the only critical point that we found. Now let's work on boundary B. And it will be a very similar process, because for boundary B, the only difference is that this curve is represented by y equals negative the square root of 4 minus x squared. So we're still going to let x equal x, but now y will be equal to the negative square root of 4 minus x squared. And so rewriting the multivariable function, we'll have f of x comma the negative square root of 4 minus x squared, which will be equal to x squared minus y, right? We're using this function right here, but replacing y with this expression. So we have x squared minus that expression squared. So let's write that in here. Negative square root of 4 minus x squared squared. But it doesn't matter that it's negative. If you square this, you'll get the same value as if it was positive. So we're going to get the same exact expression here that we got over here. A negative number squared is positive, and then the square root and the square cancel out, just leaving you with minus 4 minus x squared. Distribute that negative, combine the like terms, and you'll get the same exact function of 2x squared minus 4. Okay, and then you want to take the derivative of that, and so f prime of x comma the negative square root of 4 minus x squared will be equal to 4x. It's the same function as before, so its derivative will also be the same. The derivative of that expression is 4x, and so then setting that equal to 0 and solving for x will give us x equals 0. And so now, what y-coordinate corresponds to that? This is where it will actually be different, because the y-coordinates for this boundary are dependent on this expression, the negative square root of 4 minus x squared. So if x is equal to 0, you'll have 4 minus 0, which is just 4. The square root of 4 is 2, but then this negative out front makes it negative, so we get y equals negative 2. So that is a different critical point. All right, last time we had 0, 2, now we've got 0, negative 2, which is also in the region, right? The point 0, negative 2 would be this point right here. So let's plug that into the function as well and get its z value. We have the critical point of 0, negative 2, which is in the region, so check that off. And if you plug that into the function, you will get a z value of negative 4. Okay, if x is 0 and y is negative 2, for this function, you will get negative 4 as the output. All right, and so now we have all the different points that we need to consider as potential absolute extrema for this function over this region. Now we just have to compare their z values and see which is the biggest and which is the smallest. And so we want to consider this critical point, these two endpoints, and then these two critical points from the boundaries. And so the biggest value of z that I see is 4. These two endpoints have 4 as their output value. And then the smallest value I see is not 0, but negative 4. Both of these 2 points have a z value of negative 4. So my final answer here is this. We have 2 absolute maximums at the points 2, 0, 4, and negative 2, 0, 4. And then we have 2 absolute minimums at 0, 2, negative 4, and 0, negative 2, negative 4. All right, that is the final answer to this example. Let's take a look at one more for this video. Alright, so for our last example, one more time we want to find the absolute extrema of the function over the region. And we're given the multivariable function f of xy is equal to 12 minus 3x minus 2y, and the region is a triangular region in the xy plane with vertices of 2, 0, 0, 1, and 1, 2. Okay, so the region that we've been given here is unlike our previous two examples, but it's nothing that we can't handle. And so let's start by graphing the region. This will be my y-axis, and this will be my x-axis. But then we're given these three vertices of a triangular region, which just means it's a triangle that connects these 3 points in the xy plane. So let's plot them. We've got 2, 0 as one of our vertices. So if this is x equals 1 and this is x equals 2, that would be one vertice right there. Then we've got the point 0, 1. And so if this is y equals 1, this would be the point 0, 1. And I guess I'll label them. That's 2, 0, and this is 0, 1. And then finally, we have the point 1, 2. So if this is y equals 2, then the point 1, 2 would be right here. All right, so I'll plot that point. That is the point 1, 2. Those 3 points make up the vertices of this triangular region. So what you want to do to finish off the sketch of the region is connect those 3 points. So I'll do that right here. Okay, that is our region R. Because it is a triangle, it has 3 different boundaries, as well as 3 different endpoints that we will have to consider when we're looking for various points that could be absolute extrema for this surface on this region. All right, but before we do any of that, we still want to check for any critical points on the function itself. So let's start with that. Let's find the first partial derivatives of that function, set them equal to 0, and solve. So beginning with fx, let's take a partial derivative with respect to x. The derivative of 12 and negative 2y will be 0, but then the derivative of negative 3x will be negative 3. And so then for fy, the partial derivative with respect to y, both 12 and negative 3x are constants, so their derivatives are 0, but then for negative 2y, the derivative is negative 2. All right, and so setting those equal to 0 gives us 0 is equal to negative 3, and 0 is equal to negative 2. And so there's no variables in those equations. Those are just straight up untrue equations, right? 0 does not equal negative 3, and 0 does not equal negative 2. So there are no critical points on this function. All right, there are no points where both fx and fy are equal to 0 at the same time. In fact, they're never equal to 0. It's always negative 3 and negative 2. Okay, so we get no critical points for the function. So there's nothing to consider there in terms of absolute extrema for this function over the region. But there are other points that we need to consider, starting with the endpoints of the region. We have 3 of them. So let's check those now. For the endpoints, we have 2, 0, 1, 2, and 0, 1. And so let's plug each of those set of coordinates into the multivariable function, starting with 2, 0, when x equals 2 and y equals 0. The function will output the value of 6. So I'll write that down here. The z value is 6 for that point. If x is 1 and y is 2, plugging those values in, you'll get z equals 5. And then for x equals 0 and y equals 1, plugging those into the function will give you an output of 10. All right, and so that's it for the endpoints. We now have all their z values for considering absolute extrema, but we can't quite make any conclusions yet because we still have to consider any potential critical points along the boundaries. And so that's what we're going to do next. I'm going to start by looking at this boundary here, which I'll call boundary A. And for that boundary, what would we say x is equal to and what y is equal to? Well, since it's not a horizontal or vertical line, we're not going to be able to just let x or y equal some constant value and then let the other one just be equal to itself, which is what we did in the first example for this video. We can't do that here. Instead, we would like to take an approach similar to our previous example, where we represented the boundary with an equation for y, right? This is a line that would have a slope that we could represent with an equation. All right, and so if we find the slope of this line, we could then set up the equation for it and then use that for our substitution in the multivariable function to find any critical points along that boundary. All right, so let's do that here. Let's calculate the slope of this line. Remember that you want to use 2 points in that line and take the difference of the y coordinates divided by the difference of the x coordinates. And so I'll just let this endpoint be the first point and this endpoint be the second point. So we'll have 0 minus 2 for the difference of the y coordinates that goes in the numerator. And then we'll have 2 minus 1 as the difference in the x coordinates in the denominator. So we get negative 2 divided by 1, which is negative 2. That is the slope of this line. So if we use that slope along with one of those 2 points, I'll use this one, we can set up the equation of that line using the point slope formula, all right? Or you could use y equals mx plus b if you know the y-intercept, but I can't really tell what the y-intercept will be for this line. I suppose you could extend the line to figure out what it would be, but if you don't have a super accurate graph, that may not be an option. So let's just use the point slope formula here. Remember that it's y minus y1 equals m times x minus x1, where x1 and y1 are the x and y coordinates of a point on the curve. And so as I said, let's use this point 2, 0. So the y coordinate is 0 and the x coordinate is 2, giving us y minus 0 equals m, the slope of negative 2 times x minus 2. So simplifying, we get y equals negative 2x plus 4. That will be the equation that represents this line, and that's what we're going to use for our substitution. Okay, we're going to let x be equal to x, and then y be equal to that line. Okay, whenever you use this method of representing y with an equation in terms of x, you can just let x be equal to x, and you're good to go. But doing that, here's what we'll get for the function. We'll have f of x negative 2x plus 4, and that will be equal to 12 minus 3x minus 2 times y, right? That's from our function here. But y is now equal to negative 2x plus 4. So we have negative 2 times negative 2x plus 4. And so simplifying, we have 12 minus 3x plus 4x minus 8. I just distributed negative 2 through this quantity. And then combining like terms, 12 minus 8 is 4, and then negative 3x plus 4x is positive x. So this is equal to 4 plus x. And so then taking the derivative of that function so that we can find any critical points by setting it equal to 0, the derivative of 4 plus x is just 1, right? The derivative of 4 is 0, and the derivative of x is 1. And so if we set that equal to 0, we get 0 equals 1, which is not a true statement. There's no variables there to solve for, so there are no critical points along this boundary. Okay, so that's the conclusion here. There are no critical points, so that would be it for boundary A. And so let's move on to the next boundary. I'm going to look at this one. Let's call it boundary B. And for boundary B, we also have to come up with an equation for that line. This time it's going to be a little bit easier because we can see the y-intercept for that line. It's y equals 1. That's where the line will cross the y-axis. And if you wanted to, you could also just count the slope from the graph. We can see that the rise is negative 1 and the run is positive 2. So the slope is negative 1/2. But in case your graph isn't accurate enough to see that, you can just calculate the slope normally. The slope m will be equal to the difference between the y coordinates divided by the difference between the x coordinates for 2 points on that line. I'll use 2, 0 and 0, 1. And I'll let 2, 0 be the first point again. So we'll have 0 minus 1 in the numerator. So I'll write 0 minus 1. And then for the denominator, take 2 minus 0. So I'll write that in here. 2 minus 0. So just as we said earlier, we get negative 1/2 for the slope. Okay, and so then setting up the equation for y is a lot easier this time around. I'm just going to go right to this step. We're going to let x equal x. And then y, we're going to use the equation y equals mx plus b. M, the slope, is negative 1/2, so that will be multiplied by x. And then we'll add that to the y-intercept, which will be 1, right? This line will cross through y equals 1, which is where that endpoint is located. So there's no need to use the point slope formula here. We already know what the y-intercept is, so we can go right to that equation. And so now setting up the function, we'll have f of x comma y, which is negative 1/2 x plus 1. So we'll have 12 minus 3x minus 2 times y, which is negative 1/2 times x plus 1. Right, just to be clear, we're rewriting this multivariable function, but replacing x with x, and then y with this expression. That's how we got this right here. Now, distributing negative 2 through this quantity, we will get 12 minus 3x plus x minus 2. And so then combining like terms, 12 minus 2 is 10. Negative 3x plus x is negative 2x. So this is equal to 10 minus 2x, and that would be the function. So now take the derivative of it. You need to take the derivative of that function, set it equal to 0 to find any potential critical points. And it's going to be a very similar story to our boundary for a, because the derivative here will be another constant. The derivative of 10 is 0, and the derivative of negative 2x is negative 2. And so setting that equal to 0, 0 is not equal to negative 2. There's no variables to solve for there, so there are no critical points. All right, boundary B produces no critical points for us to consider as potential absolute extrema, which leaves us with just one more boundary to check. And that would be this boundary, which I'll call boundary C. And for boundary C, we will once again want to calculate the slope for that line so that we can create an equation for y that we can then use for our substitution. And so let's set up that calculation. Again, if you have a good graph like mine, you could just count the slope. You can see here that the rise is 1 and the run is 1, so you have 1 divided by 1. The slope is 1, but if you'd rather just calculate it, we're going to use these 2 points. So take 2 minus 1 for the numerator. That's the difference of the y coordinates, and then divide by the difference of the x coordinates, so we'll have 1 minus 0. So we have 1 minus 0. Simplifying, you have 2 minus 1, which is 1, 1 minus 0, which is 1, and 1 divided by 1 is 1. So the slope is 1, and we don't need to use the point slope formula here because this line also has a y-intercept at 1. Okay, it crosses through the y-axis at 1, so we can just use y equals mx plus b, and we will be letting x equal x and y equal mx, or 1 times x, which is just x, plus b, the y-intercept, which is 1. All right, so we're letting y equal x plus 1. So now making the substitution and setting up our multivariable function, but in terms of just x here, we're going to have f of x, x plus 1. So we will replace y with x plus 1, giving us 12 minus 3x minus 2 times y, which is x plus 1. So simplifying, 12 minus 3x minus 2x minus 2. And so adding like terms, negative 3x and negative 2x become negative 5x, and then 12 minus 2 is 10. So this is equal to 10 minus 5x. And then to find the critical points, you want to take the derivative of that. And again, we will just get a constant like we did for the other boundaries. The derivative of 10 is 0, and the derivative of negative 5x is negative 5. So setting that equal to 0, you get 0 equals negative 5. That's not a true statement. So just as with the other boundaries, we do get no critical points along boundary C. Okay, so there's no additional points for us to check. And so now we checked all 3 boundaries. Unfortunately, none of them gave us any extra points to consider as potential absolute extrema, but don't assume that that will always be the case when working with a triangular region. Depending on the multivariable function that you're working with, when you make those substitutions, you will get expressions that result in more critical points. It's just that it didn't happen in this example. Okay, so don't think that there's a pattern here that triangular regions will always result in no extra critical points for the boundaries. That's not true. You always want to check the boundaries no matter what region you have and no matter what function you've been given. Okay, I just wanted to make that clear. But with that being said, there's only 3 points to consider here. We went through the critical points for the function itself, there are none, and we went through the critical points of the boundaries, there are none. The only points there are to consider as absolute extrema are the endpoints, and we have 3 of them here. So just look for the biggest value of z and the smallest value of z, and those points will be the absolute maximum and minimum. And so in this case, 10 is the biggest value of z I see here, so that point will be the absolute maximum, and 5 is the smallest value of z that I see, and so this point will be the absolute minimum. And so let's write that out. My final answer here is that there is an absolute max at the point 0, 1, 10, and an absolute minimum at the point 1, 2, 5. All right, that is my final answer to this example. Okay, so hopefully these 3 examples, along with the examples in the lesson video for this topic, give you a good variety of different regions that you may see or work with in these types of problems. Unfortunately, these problems are pretty lengthy, so this is the last one for this video, but if you do want to get some more practice, I do have another available on my membership site, and so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.